So let's have a look at question 1 together. Now it's a bit of a mess, so we'll start to read, but we're going to stop very quickly because it's going to be too much to hold into our heads. We'll need a better tool to understand it. It says, a particle of mass 4 kilograms, okay, so far so good. That's okay. Moves from rest under the action of a force whose magnitude after blah blah blah. Okay, stop, right? Now, you could start to write down conditions when t equals 0, etc., etc., etc. But it's going to be much easier to just try and chart what's going on in terms of what is the particle doing? What kind of behavior is it exhibiting? Okay. So if I graph velocity versus time, I hope that you'll see as we progress through the questions why velocity makes sense as an axis to choose. Okay. What is happening to this thing? Well, it moves from rest, okay? So on my graph, where should I start? I should start at the origin, right? At time 0, velocity is 0. Okay? It moves from rest under the action of force whose magnitude after, and then it gives you an equation, okay? Now here's the point. It's moving. It's moving. Okay? It's speeding up, okay? Or it's moving somewhere. Now, the particle moves and moves and moves, and then it reaches a certain speed, 19.6 meters per second. Okay? Then what happens? The force ceases. So velocity is not going to change after this, right? The particle continues at a constant speed, that speed, for 5 seconds. So it looks like this. There you go. So far, so good. Remember, this is not a displacement graph, not displacement time. This is velocity. The thing is moving, but the velocity isn't changing. Okay? So at some time, which I don't know what it is, it stops, the force stops acting, right? And then for 5 seconds, it moves at this constant rate. It moves at this constant rate, right? So whatever this time is, after 5 seconds, that's when the behavior changes again for the final time. It's then brought to rest, so this is gonna come back down. It's brought to rest by a constant force of 5 kilograms weight. Brought to rest. So it's gonna come down at a constant rate, right? Something like this. Okay, there you go, I'm finished, right? Start from 0, a force starts acting, it gets to a certain speed, force stops, 5 seconds elapse, then a new force, totally separate, you can see the equations are completely different, acts on it and brings it back to rest. I don't know when it rests, but it'll be some time that I'll need to work out later on. Okay. So you can see here I have a piecewise function, right? To make it a bit easier for me, I'm going to name these different sections. Okay. So I'll call this one section 1, okay. This one section 2, and then I have my last section here. Okay. Let's take them one at a time. How far does he go? That's the question, right? So let's have a look at let's have a look at the first portion. Okay? First portion. Now, we start with force, right? Because they give us an equation for force. So I've got force equals ma, right? Now, for this part of it, they give us a force equation. They say it's 6 minus 2t kilograms weight. Now, stop, kilograms weight. Mass, that's kilograms. Acceleration, that's meters per second squared. So this side of the equation, the MA side, it's in newtons, right? But then this is not in newtons, right? It's not in newtons. In fact, it's in kilograms weight, which is 9.8 times bigger than newtons, okay? So I've got this scale happening, okay? Is that all right? Let's think about this. The force, right? The force is 6 minus 2t kilograms weight. So that's why it's big. I need to get, this is in newtons, right? This side is in newtons, and this side is in kilograms weight, but I don't want them to be different, okay? So if you like, if I said, for instance, you've got like x, let's see, kilograms, just think of weights, okay, equals 1,000 grams, right? So in fact, what's x in this case? It's 1, right? Because it's 1,000 x grams, okay? So I've got tiny, tiny units over here and big units over here. So that's why I multiply to compensate, okay? So kilograms weight are bigger than newtons. They're 9.8 times bigger. Okay, so that's where it's going to go. Is that okay? Good. All right, then I have a mass of 4, and I don't know what acceleration is, okay? But that's okay. I can rearrange this thing. Let's divide, let's see here. If I divide this by 2, and then I divide this by 2, I'll have divided by 4. Is that okay? So I'm going to get acceleration is 4.93 minus t. You happy with that? Okay, now, where am I trying to go? Now I have an acceleration equation, and it's in terms of time. Remember, we have all of these fancy ways of writing acceleration, right? The question I'm trying to answer is total distance. So what do you think is the most direct path to get there? Now, I've got 2 pieces of information. Where I'm going, like this is what I'm trying to find, and what I've got it in terms of, okay? Now, it's in terms of time. So therefore, if I'm going to integrate, I have to integrate with respect to time. So therefore, that leads me to think probably dv dt is the most helpful way to say it, okay? If I'd written like say v dv dx, I'd then be like, oh, okay, I'm kind of stuck because I don't have other things in terms of x to go with that, okay? So there we go, I've got this, okay? Now, because other parts of the proof of this are going to take a little while, I'm going to cheat a little bit, and I'm just going to go straight to here. I know there's a constant, but you can see why it's 0, right? Can you see why it's 0? It's because I have this value, right? So you can go ahead and you can evaluate it. Not that big a deal. That's the velocity equation you're going to end with. What do I do with this? Where do I go from here? Remember, like, what am I trying to do? I've chopped this thing into 3 different parts of the journey, right? So in order to work out how far I've gone in this part of the journey, well, you kind of need to know how long that part of the journey lasts. Does that make sense? Right. So how do I know? How will I work out when the journey, this part, section 1, how will I know when it ends? Good. The question says, when the particle reaches a speed of 19.6, and you can read it off your graph, right? So I can say, right, well, okay, well, let's put that in, right, 19.6. This is what I'm trying to solve now. I'll get a time, namely, I'll get time 1, right? That's what I'm going to get. 19.6 divided by 4.9, very conveniently, is 4, okay? So now I've got 3t minus t squared on 2. Rearranging, tidying up to make the quadratic a bit easier to solve, I guess I'll multiply by 2. T squared minus 6t plus 8 equals 0. Okay, you're factorizing, you get what? T minus 2, t minus 4. Okay, so you've got 2 sensible solutions. Okay, but of course the one that you're after is this one, right? Because as soon as you hit that, you've hit the requisite speed. Okay, is that all right? I guess what that would mean is if it hadn't have stopped, it would have kept on increasing and then come back down to 19.6. But we're not interested in that part. Okay, so I say, okay, t equals 2 is the valuable thing. So that's really good. I've worked out what this time is. What do I do with it? What I'm trying to find is displacement. I'm only on velocity, so I've got to climb up the ladder one more time. I have a particular value in mind. I want to go from 0 to 2, so it's a definite integral, right? The distance for section 1, okay, is going to be from 0 to 2 of v dt, right? Okay? So, no big deal. You can crunch through that. I think the answer you should come up with is this. Once you integrate properly, get the right primitive and chuck in your upper and lower boundaries, okay? And you can go ahead and you can verify that. Okay? So now what? What do I do at this point? Well, I only did the first section of the journey, right? The first 2 seconds. Now I have to work out the rest of it, okay? So I can say, well, section 2, as it happens, is really easy. It's kind of trivial, right? Distance, the distance for this part of the journey, distance, at least as far as I remember, is speed times time, right? Speed times time. 5 seconds is how long he's going for that constant part of the journey, okay? So 5 times, what did I say, 19.6, okay? What is that? It's like, oh, I don't know. 5 times 19 is 95. 5 times 0.6, 98. I think that part's easy. Last part. Okay. Now this part is very similar to what we had here, right? Again, they give you a force equation. So I'm still going to have F equals ma even though it's a different force, okay? The equation they give you, let's see, where am I up to? Is that it's a constant force of 5 kilograms weight. 5 kilograms weight? Now, pause for a second and look up. 5 kilograms weight. It's 5. It's 9.8 times bigger. What's the mass? Still 4. That hasn't changed. And then there's acceleration. Right? I'm missing something. What am I missing? Look carefully. Read the question again if you have to. What's wrong with this line? Something is drastically wrong.
It should be a negative.
Aha! Why? Why should there be a negative? It's very common sense when you think about it. What's this force doing? What's this force doing? It's speeding you up, right? It's speeding you up, so positive direction, right? But the question says, at that end point, it's then brought to rest. So whatever this force is doing, it's got to get it away from being at a constant speed, get this velocity back down to 0, okay? So hence a negative, right? From there, you can solve, okay? I think that's 49, if I remember it right. So you've got that acceleration, okay? Now you have to be a little more cautious because when you integrate, you better believe that constant's not 0, right? How do I work out what the constant is? I just gave you a clue in case you hadn't noticed. How do I work out the constant? Because it's not 0. Ah, good. I have a condition. That one, right? It has to be this one because it's got to be in section portion 3, right? That's when this rule takes over, okay? So I can say when t equals 7, right? When t equals 7, this point there, after the first journey, 5 more seconds, then the velocity is 19.6, okay? It turns out a bit gross. The numbers aren't very friendly, but you work out the constant, and I think you should end up with this. Yuck. But at least it's not a repeating decimal, okay? So now I have the velocity equation for the last part of the journey, okay? The velocity equation is this, plus, okay? What do I do with this thing? What do I do with that? Think back to how I dealt with section 1. I want to get towards integration, but I don't know what to integrate between. I know where to start, right? But I don't know what this final end time is. But it's not that hard, is it? It's just like the question we just looked at. You've got to work out when v equals 0, okay? So you're going to solve for v equals 0 here, okay? When v equals 0. You go ahead, you crunch the numbers. I'm pretty sure it's 8.6. Okay, double check it, confirm it. But this is not the hard part of the question. This is just the crunching part of the question. Okay. What do I do with this value? No, seriously, what do I do with this value? I have to integrate again, just like I did here. Okay. So distance 3. It's going to be the integral from where to where? 7 to this new time that I've just determined, 8.6. That's the end of the journey. And here is my velocity equation. with respect to time. It's a little bit more messier because unlike here where you had a 0, you can just go ta-da, it disappears, okay? But here you still end up getting, your calculator can take care of it. I'm pretty sure that's what you land on, okay? That's how far it travels back towards, okay, you get the idea. So what's the answer? I've got distance 1, I've got distance 2, and then I've got distance 3. You add them all up, and you get this, which is somewhat convenient, but anyhow, there's your number. So I think they rounded off to 1 decimal place in the textbook. That's what they were looking for. Okay?